In that case, hello everyone. My name is Wei Ming, and I'll be presenting like the first half of DSU 2. Last time or yesterday we covered disjoint sets, or DSUs for short, and today we'll be covering a couple of extensions or other ideas that draw from knowledge and general motivations behind DSU. So these ideas include, or last time we covered DSU path compression and merge by size, two optimizations that if each used separately would improve the complexity of queries of the root and merges to O of log n per query, and if used together will improve the complexity to O of inverse Ackermann, and the minimum spanning tree by Kruskal's algorithm, which is one application of DSU. So starting, we'll first cover small to large merging, an application of the union by size idea in a DSU. So to start, here's our example problem, which is to determine the number of unique colors in a node subtree. So you're given a tree of n nodes. Every node has a color, and your task is to find the number of distinct colors in the subtree of a node. So for instance, we can see that in the subtree of node 7, there are two distinct colors, being red and blue. Even though red occurs twice, it only is counted once. So could someone tell me how many distinct colors are in node 2's subtree? Sure. Oh, yes. There are four colors, being green, yellow, blue, and red. So does this problem statement make sense to everyone? All right. So we can have a naive solution where we maintain for each node a list of colors that are present in its subtree, or a set of colors. So we can we remove duplicates in advance, and we can determine the list of colors for a specific node by merging the color lists for their children together with each other. And of course adding the color of our current node as well. So this is described here in the piece of sample Python code, where we run a DFS to determine the set of colors in node U subtree, and we initialize colors to be a set consisting only of the color of U. Then we loop over all the children in node U subtree. We first DFS recursively into that child V subtree to get the color list. Then for each color C in that color list, we add it into our own current color set. And finally, we can determine the answer for node U as the length of the set, as the set removes all the distinct elements, and we return the set to recursively feed the parent's call to our DFS function. So does this sample code make sense for how it will solve our problem? So in that case, I guess the first question would be, what would the complexity of this code be? It's not too obvious, as we can see there are nested for loops, returning sets, and whatnot. Does someone have a guess at the time complexity of this code? Yeah. Sure. We assume that in Python, inserting to a set takes constant time. But yes, it would be n squared. And the reason for this is we can see that the set of colors can have a length at most n for any specific node. This is because in a node, we can just assume it has decently large subtree size and a decently large number of colors. And we have to run this process of finding the list and moving the colors from the child into our current list for every individual node, and multiplying for n DFS calls, moving at most n colors, we end up with an O of n squared complexity. Does this make sense to everyone? So complexity is O of n squared. And we can see that the bottleneck in the time complexity mainly comes from the part where we are merging the sets of colors. As you can see, the bottleneck really is in for every single node that's a child, and for every single color that's in like the set of colors corresponding to that child. This really is the bottleneck in our solution, and I think what we should do is try to optimize.
Thank you.
Oh no, I was muted. Okay. Okay. So what we should do is try to optimize this specific What we should do is try to optimize this part where we're merging the colors into merging the colors of the children into our colors array. So we can take a quick detour to just simply talk about the process of merging two sets, where if we want to find the union of two sets A and B and then write it into A as we want to do, as we can see here, we're finding the union of the set colors and child colors and then writing it into the colors set. So if we want to do the same thing for sets A and B, there are two methods of doing this. The first way is we merge the elements in B into A in O of size of B time, or alternatively, we merge the elements of A into B in O of size of A time, demonstrated by these two pieces of pseudocode here. Where in method 1, we just iterate over the elements in B and just add them to A. In method 2, we iterate over the elements in A, add them to B, and then we set A to be B. And notably, it's important to make this distinction that we can merge it in one of two ways, because borrowing from the knowledge we covered yesterday in DSUs, it would make sense that we try to merge the smaller one into the larger one. Oops. Yeah. We try to. It makes sense for us to merge the smaller list into the larger list. As you can see that this process of analyzing the number of times a color moves is very similar to the process of analyzing depths, like the maximum depth in or the sum of depths in a disjoint set. Wait. Yes.
How long does A plus B take?
So we assume it takes constant time, or at least in Python specifically, I believe due to how references etc. are done, we assume this takes constant time. For languages like C++, we can do a dot swap B or swap A and B to write what B is into A in constant time.
So does A plus B work in C++?
A equals B does not work in C++, but we can instead do something like std swap A comma B to do this part in constant time. Thank you. So we can borrow some of the knowledge that we used from DSU, which is that when we're merging the smaller element into when we're merging the smaller set into the larger set, it's very similar to how in a DSU we have union by size. And again, and here, like for instance, we can see that when a color X, in quotes, moves lists or moves sets, it will join a list with twice X's original list length. Right? I should have mentioned. Here we assume that the worst case scenario is if all the colors are unique, and it makes sense intuitively that this is a worst case because if the colors weren't unique, at some point, two colors will cancel each other out. One of the colors could have just existed to cause more problems later on down the line. And we can see here that, for instance, when we see color 6 joining the set that contains color 3, it'll make I colored it wrong. It'll make the new list 3 6, which has double the length originally of 6. And when we merge the lists 3 6 7 with 1 2 5 4 8, we will end up with the new list 1 2 3 4 5 6 7 8, which has length more than double the length of the set 6 was originally a part of. Does this make sense? So again, it's very similar to how in a DSU when you do when you do union by size, as you move from a node to its parent pointer, the size of the subtree will have doubled. basically an identical thing holds here, that when a smaller set is merged into a larger set, the size of the resulting set had to have at least doubled relative to the size of the smaller set. Does this make sense? Okay. So in that case, supposing this is a case, does someone can someone tell me how many merges will happen in total? Well, after we employ this optimization. Yeah. Yes. Yeah. So a specific element will be merged O of log n times and summed across all of the nodes throughout most O of n log n movements. So as a result, because adding into a set in Python takes O of 1 time, our found complexity will be O of n log n. Does this make sense to everyone? Okay. Yeah, and then here's a piece of pseudocode demonstrating what we want. There might be a little bit of errors because I'm not the most familiar with Python, but the general idea is you start by again initializing colors to be a set only consisting of the color of U. Then whenever we process each of the children, we first determine the list of colors within that child subtree. Then we compare the two sets of colors and child colors to see which one is larger. And if colors is larger, then we'll merge the elements in child colors into colors. And if child colors is larger, we'll merge the elements in colors into child colors. And then set colors to be equal to child colors. And finally, we can set the answer of U to be the length of colors. And we return colors to recursively feed the previous call to this function. Yes, so does anyone have any questions about the code or about what I just presented? Cool. So here we have another problem that can be solved with small to large merging. So you initially have a graph of n nodes, and there are no edges. And over the course of the following m days, we will build one edge every day. And your question is to answer Q queries of the form A, B, or you're given A and B, and you have to find after how many days can we first travel from node A to node B. So I have like a couple of examples. So I consider this is our graph. We initially have 5 nodes, no edges between them. On day 1, we add an edge from 1 to 2. On day 2, we add an edge from 2 to 3. On day 3, we add an edge from 1 to 3. Day 4 from 4 to 5, and day 5 from 5 to 2. And then so I consider here's an example. Oops. Is there a way for me to get rid of that? This is not out of the way. Okay. Oops. So for instance, suppose we want to find the first day that nodes 1 and 3 are reachable from each other. We can see that on day 0, they're not reachable from each other as there are no edges between them. On day 1, node 1 can reach node 2, but not node 3. And finally on day 2, after we add the edge from 2 to 3, there exists a path from 1 to 3, being going from 1 to 2 and 2 to 3. So does this problem statement make sense as presented? So in that case, can someone tell me what would be the first day nodes 2 and 4 are reachable from each other? Or just hold up your hand number, your fingers being the answer. Yeah. Yes, it would be day 5 after we add the edge from 2 to 5. Then there would be a path being 4, 5, and 2. So here are a couple other examples. For instance, nodes 4 and 3 are first reachable from each other on day 5. Nodes 4 and 5 are reachable from each other on day 4. Or nodes 2 and 5 are reachable from each other on day 5. in a sense, as similar to what we covered yesterday, when we think about problems, especially dealing with like reachability of two nodes, it's often useful to think about them in the context of a DSU, because a DSU is the structure that maintains reachability as we add edges, and it can also tell us what edges are not useful when editing like reachability as a whole for the graph. For instance, let's suppose we want to like find the answer for the query with a is equal to 1, b is equal to 4, and on the left you can see the ds. Yeah, on the left you can see the regular graph, and on the right you can see the DSU corresponding to the graph as we add edges over time. So for instance, after day 1, we add an edge from 1 to 2 in our graph, and we will direct the parent pointer of 1 to be 2 in our DSU. And we can also see, like, for our example queries 1 and 4, they're not reachable from each other. And our DSU also tells us the same thing, because the head of the connected component of 4 is 4, but the head of the connected component of 1 is 2, and the two things are still not equal to each other. So on day 2, we add an edge. Again, the nodes are still not reachable from each other. On day 3, we add an edge, and we also see from the DSU that the edge that we added from 1 to 3 doesn't actually change anything. On day 4, we would add an edge from 4 to 5. Now the root of 4 would be 5, but the root of 1 is still 2, and the two things are not equal to each other. And finally, on day 5, we can see that 1 and 4 are in the same connected component, as evidenced by the fact they all have a root of 2, and in the graph, the two nodes are connected to each other via the path 4 to 5, 5 to 2, and 2 to 1. So does this example make sense? Of just like handling a query with the help of a DSU. So this kind of tells us that, or in a sense, so suppose we took every query of the form AB, where we have to find the answer for like reaching node B from node A, and we split them into 2 half queries and put them into nodes A and B. So here we can see that query number A, I use letters so it'd be less ambiguous. Query number A, or colored in green, corresponds to A, B being 1, 3, and we would split them into 2 parts and initially put one of them into node 1 and one of them in node 3. And we saw, like in the previous example here, that we can also think of the process of having 2 nodes being connected as these 2 parts of the DSU belong to the same connected component. So we'll keep them in these half query states, and over the course of adding edges, we'll try to find out at like what time these 2 half queries can join together, and that will clue us in on exactly what the answer is, what the answer for that specific query is. Like we can see that the answer for the query 1, 3 will be determined when we can find out when 1 and 3 are in the same connected component. So we do something similar for query B, which is 4, 3, something similar for query C, 4, 5, and query D, 2, 5. They're split into their individual half queries and put to the nodes, and just put as a list corresponding to the nodes the queries are a part of. So here we'll again have the graph on the left and the DSU on the right as we try to add edges, and we can see how splitting half queries can help us answer our queries. So initially, again on day 1, we'll add an edge from node 1 to node 2, and we'll move the query list that was originally on node 1 into node 2, as 2 is now the root of 1, and it's helpful to store useful information for connecting out components at the root, because that's where all the nodes will direct to. Now we can see that on day 2, when we direct the edge, so when we add an edge from 3 to 2, or in our DSU, we direct the edge from 3 to 2, and we merge the elements in node 3's list with node 2's list, we can see that the two half queries corresponding to query A are now in the same list with each other. And this is the first time when this happens, so we can find out. So this tells us that the answer for query number A is 2, corresponding to the fact that's currently day 2. Does this make sense? Oh, like show of hands. Does that make sense? Cool. Okay. Then we can see on day 3 again, nothing happens in our DSU because the edge added from 1 to 3 is redundant. Then on day 4, when we add an edge from 4 to 5, we'll merge the list that was originally on node 4 with the list that's currently on node 5. As we add an edge from 4 to as we point 4 to 5 in our DSU. And again, we can see that now the two half queries corresponding to query number C are in the same list with each other. And this tells us that the answer for query number C is 4, corresponding to the fact it's currently day 4. Right. I forgot to mention this earlier. After the two half queries are in the same list, or we can just remove them because they're not helpful. They're not helpful for answering queries later on, as their query has already been answered. And then being the list will contribute to the overall speed of the code later on. So after we answer query number A, we can remove it. So now we can see that the answer for query number C is 4, as on day 4, the half queries corresponding to query C are in the same connected component with each other. And finally on day 5, we merge what's left of node 5's of connected component rooted at 5's list, which was D, B, with the list at node 2, which is also D, B, since we added an edge from 5 to 2. And we can see that the answers for these queries are all 5, because on day 5, these half queries have joined together in the same list. So does this example make sense? Okay, great. So this, in a sense, will tell us our algorithm, or this, in a sense, tells us that our problem can be solved with a DSU. And initially, we can split each query into the two half queries and put them into the corresponding lists. I just realized I had a typo in this slide. It's okay. So we read in A and B as input. It should be queries of A-1 dot add I. So we add I into the set of queries corresponding to node A, and we add I also into the set of queries corresponding to node B. Then over the course of over the course of the following m days, it should be m instead of n. We can determine the edge that we built on that specific day. Then we can merge u and v on that day. The merge function is on the next slide. And finally, we can go through and print the answers. And notably, one of the very helpful things for this problem is that we aren't required to answer each query immediately after we received it. We can instead choose to process the queries and answer them in an order that's fitting for us. And that is what really makes this technique workable on this problem. So does this overall code structure make sense, ignoring the fact that I haven't written out the merge function yet? Cool. So here in our merge function, we can see we read in like x and y as the two nodes to merge, and day as the specific day it currently is. Then in like a regular DSU thing, we first set x and y to be the roots, and if they're equal to each other, we just return. Oh, okay. They just return, and if the size of x is less than the size of y, we swap the two. Then for all the queries in node y, because y is the node, as we can see at the bottom, we'll be setting par of x to be equal to y. So we'll transfer all the elements in node y's queries into node x's queries. So we first check if h is already in queries of x. So for all the h, like h for half queries, in queries of y, we first check if h is in queries of x. And if it is, that means that these two half queries have joined together are in the same list now. In that case, we can determine what the answer for h is, which would be day, and we can now erase h from the queries of x. And otherwise, we can add queries of x. Otherwise, we can add h into queries of x. And then finally, we update our DSU to we update the sizes and we update the parents. Does it make sense, everyone? So we can see that this is very similar to our DSU, the DSU code that we had from last lecture, except we've added this block in the middle to deal with the queries, as we found that the DSU was a natural way to store and maintain these queries. And actually, we can notice that when we do union by size, we're actually also doing small to large. Because every single time a query, in quotes, moves lists, it has to join a new connected component with twice the size. This is because we are doing union by size. And this, again, also guarantees O of n log n element movements, as each individual element cannot move more than O of log n time. So this actually just gives our final complexity as O of n log n, as there are only O of n log n element movements. Does this make sense? Great. So here we saw another problem where we can apply the small to large technique, or just union by size, and use it to solve a problem that may not immediately immediately not be clear that a DSU is the best way to approach it. All right. Thank you. I'll now turn it over to Larry to go over dynamic connectivity and offline deletion trick.
Okay, so we've seen how we can use DSU to maybe solve problems where perhaps we have a bunch of insertions, but our queries might be a little bit harder to figure out. Here, I'm going to talk about a technique where we can actually delete edges from our from our graph. And what do I mean by this? Well, for example, let's consider our standard DSU problem from last week, where you can either merge two teams or query whether A and B are on the same team, but now we can essentially click an undo button. So we can undo the last merge that we made between team A and team B. Well, how might we do this? Well, as you might figure, to do this, we do something very similar to our original DSU, where essentially we can handle the first query by calling a DSU join, and we can handle the second query by figuring out whether their roots are the same. So all we need to figure out is how can we augment this data structure to be able to fit this second query. And the idea here is we want to actually keep a stack of all the changes that end up happening. So for example, in the code on the right, what you see is that we just have the standard merge by size DSU, where you have the root function, and in the join function, what we do is we merge the smaller one into the larger one. But as you can see, we have a couple of additions in here, and what those do is essentially we store all the changes that we make when we make a merge. So when we make a merge, we change the parent of y to be x, and we also update the size of y to be, or the size of x to incorporate the new elements. And so when we roll it back, we can just pop the last change off of the stack and then modify the changes that we made accordingly. What you might notice here is, well, in our root function, we're directly just doing the naive root function. We're not actually doing path compression. Why might this be? Why would we only use union by size when we're doing a data structure like this? Does anyone know? Yeah?
Maybe because it'll, if we do path compression, that will remove information about, the order in which things were added.
That is a good idea, but it's not quite exactly why we don't do it. So, for example, we're keeping track of the changes that we make to the array, right? So, what happens during path compression? We keep changing the array, right? So, if we keep changing the array during path compression, then that adds a lot of new changes that we need to also roll back when we roll back our changes from a join. And in fact, if we don't use small to large, the amortized complexity analysis from path compression doesn't work because you essentially get an expensive operation that normally would get fixed by doing the operation, but then you can just roll it back and do it again. And so you have just all these expensive operations that you just keep doing and then rolling back, and that causes your code to be slow. So in general, when we code rollback DSU, we only use union by size to make sure the amortized complexity doesn't break. I guess as an example, we can look at an example graph. So here, for example, we're adding an edge from 6 to 7, and along this process, we first change the parent, we update the size, and then we append it to the top of our stack. And now if we wanted to add an edge from 2 to 0, we do a similar thing. We update our size, we update the parent, and then we append it to the top of our stack. Similarly, what happens when we add 5 to 7? So we append it to the top of our stack, then we modify the sizes and parents respectively. And so what do you guys think might happen if we wanted to roll back the last edge that we added? What would we change here? So we just added an edge from 5 to 7, and now we want to roll it back, right? So what would change within our parent and size array for us to be able to do this? Yeah?
Parent of 5, go back to 5, and then the size of 7 minus the size of 5, which is 1.
Yeah, so exactly that. So now that we remove the edge from 5 to 7, we set the parent of 5 to be 5, and then we modify the size of 7 to be the size before we added 5, which is the size of 7 minus the size of 5. Okay, well, let's try adding a couple new edges. So we add an edge from 5 to 8. We add another edge from 7 to 8. And now let's say we want to roll back this edge. Does anyone want to do this one? Yeah?
So we set the parent of 8 to we set the parent of 5 the parent of 7 to equal 7.
Uh-huh.
And then we do the size of 8 minus equals the size of 7.
Which is 2.
2.
Yeah. So that's exactly what happens, right? So we set the parent of 7 to be 7, and then we set the parent of 8 to be the size of its current tree minus the size of the thing that we added to it, and that gives us 2. So this is kind of how rollback DSU works, and what we can do with this is we can actually extend this idea to be able to solve a much more complicated problem in a similar vein, which is the problem of dynamic connectivity. So what is this problem? Well, now, instead of being able to undo the last edge that we added, we add an edge, and then we just simply remove an edge, any edge that has been added. And we query whether A and B are on the same component. And so now, can anyone tell me why, for example, directly applying DSU with rollbacks isn't going to exactly solve this problem? Anyone? So the idea here is that, suppose that, we have this graph of, all of these things, right? And we've added, first we added 6, then we added 2, then we added 5, then we added 4, then we added 8. Okay, so now let's say we wanted to get rid of the edge from 6 to 7. How would we do this, right? Well, there's no easy way to just, roll it back because it's very far down in our stack. So the best we could do with DSU with rollbacks is roll back all of the operations until we roll back the operation with 6 to 7, and then add all of the operations afterwards back on top. And so this is problematic because 1, it's slow, and 2, it doesn't exactly solve what we want it to, or it doesn't actually do what we want it to do. So we need to find a new approach. And to do this, let's consider an example. So here what I'm doing is I've laid out all of the like potential queries where we insert, delete, or insert or delete edges, and then at certain times we want to query whether nodes are connected. And what we can notice if we play around a little bit with this sample is that every edge we add is defined exactly by a range of times. And it's the range of times it's active in the interval, which is the time when you insert it to the time when you delete it. So this is the only time when this edge is going to be active within our graph. So for example, if we consider the edge from 1 to 4, then at time 1, it's not active because we haven't inserted it yet. But now, once we reach time 2, we've inserted the edge. And so now, what happens is it's going to remain in our graph until time 5 or until time 6 when we delete it. And so what this allows us to do is this allows us to reduce this like rather complicated problem into a simple range query problem, where now every edge represents an update to a certain range, and we want to somehow be able to solve the problem at every given time step. So let's use a segment tree. So again, consider like, for example, the edge from 1 to 4, and now we build a segment tree over this time, right? So now, for example, if we wanted to add an edge, or it's kind of like doing a query with a segment tree where, like, let's say you wanted to query from 2 to 5. Well, what you would do is you would go down the segment tree until you reached the, the magenta like blocks, and within those blocks you would find the answer and then combine it with your previous answers to get the overall answer. Here, what we're doing is we just insert 1 to 4 into all of these magenta blocks. And so similarly, for a different edge, like 1 to 3, we can add it to its corresponding block. And so, does everyone understand how like we can add these edges so far? Okay. So now, once we have all of the edges added, we can essentially just walk along the segment tree. And I'll explain a little bit more about what exactly this walking constitutes. But essentially what we do is when we're at a node, we recurse down into the subtrees, and then because we know that the edges within that node are going to be present along all of the like timestamps represented by the node, we can add it at the very start. We recurse down into the subtrees. Once we answer all of the queries and we want to go back out of the node, we roll it back. And so, for example, if we have the following example, this is like the same example as before, except I put all the edges onto the segment tree. So now suddenly you see like if you have a DSU and you have like the edges, we add all the edges at the node into our DSU. So our DSU currently has 1 to 2. We recurse into its subtrees. So let's say we want to recurse into the left subtree, and then we add all the edges here. We recurse into its subtrees. We add all the edges here, and then now suddenly we're at a leaf. And once we're at a leaf, we have generated essentially the entire DSU of this graph. And so we can now answer all the queries at time 1 using this DSU. And so when we go back out of it, we go back out, and then we roll back all of the edges that we added. And so now we can go into the next subtree. So now we go into here, we've added 1 to 4 as an edge, and now we can query our, for example, at time equals 2, are 2 and 3 connected? Does anyone want to answer this? Yeah?
No.
Yeah. We can see from our DSU that, 2 and 3 are clearly not connected at time equals 2, right? And so we can just keep recursing. So we go back up and we roll back all of the, so when we're here, we added 1 to 4. So once we leave it, we roll back the 1 to 4 from our DSU. And now when we go back up, we roll back all of these edges again. And now we go to the next subtree. So we go here. So when we enter it, we add 1 to 4, and then we recurse. So we go here, we add 2 to 4, and now we have, we can answer all the queries at time equals 3. So now when we go back up, we roll back our last edge, and we go into the next subtree, and so on, and so forth, and whatnot. And so if you look at the code, this is exactly what it's doing, where in our insert, we're essentially just doing a segment tree update, where we add the edge to every single node that corresponds to this range. And then when we solve, we do this walking along our segment tree, where we add the edges corresponding to a node, then recurse into its subtrees, and then when we go back out of the node, we roll back all the edges that we just added. Yeah?
The solve function should be edges of I.
Oh, yeah. It should be edges of I. Yeah. It's a good catch. Yeah. So basically what we're doing is we're just walking along our segment tree, and every time we reach a leaf, we can answer all the necessary queries to answer, and then when we go back up, we roll back all the edges that we added. Does that make sense to everyone? Okay. So that is the end of our lecture. The problems will be posted shortly. If you have any questions, as always, feel free to ask. And we will also be handing out prizes for the raffle today. So make sure you stay for that.
Maybe I should edit these slides. I'm going to add the feedback. Oh, we can do a Q&A since lecture time is there's still like 10 minutes. So we can go back to, there's kind of 3 parts here. So questions on dynamic connectivity or rollback DSU or the new roads queries. Yeah. Oh, first slide.
Can you go over the rollback again?
Yeah. Okay, so when we roll it back, essentially what we're doing is we are like keeping track of all the changes that we make. So in our join function, you can see like if the roots are the same, that means that we don't make any changes, and so we can insert a dummy variable into our changes list. But if we do change something, then we insert that exact change into our changes list. And then when we roll it back, we can just essentially roll back exactly what that change was and then undo it, if that makes sense. Any other questions? Yeah?
For rollback, if you only allow one undo, then could you implement optimization with root? Because wouldn't that not affect?
Well, the big problem with path compression is that you now like not only change things when you do a join, you also change things when you do a root function. And so what ends up happening is you're going to saturate your like changes array with a bunch of changes that actually happen when you call the root function, for example, for queries, that you'll also need to undo before you can undo your update.
What I was saying was, like if you're only calling join once,
Uh-huh.
to undo instead of undoing like multiple times in a row,
Uh-huh.
then when you call root of both nodes, wouldn't it just change like the nodes in the subtree to be the have a root equal to the like original nodes, but then when you connect that to the
Yeah, I guess I think I understand your question, and I think like the problem here is that like imagine you have a subtree like this, right? And now you join it into a different subtree, and like you join it, right? And now you have a couple queries. Let's say you query some node in this subtree and some node in this subtree, and eventually what happens is through path compression, it just remembers, oh, I should point directly here instead.
Oh, okay, because
Yeah.
the queries will.
And now you want to roll it back, but the problem is you've already pointed this over here. So you actually have to roll back these changes first before you can roll back this one.
Oh, okay. So it's because the queries will also.
Yes.
Okay,
That yeah. Does anyone have any other questions?
Yeah, there were a couple. Yeah, for the future there. I remember seeing one or two more hands at the top of the way.
Oh yeah.
But on this, do you have an example where it's like excessively more than longitude?
Okay, so the thing is, if you use union by size and you can and you still roll back your root function every time you call it, it actually still remains O of log n. It's just a lot slower because you've added all these extra rollbacks that you need to do every single time, and so it's just advisable generally to only use union by size. And for example, if you only use path compression, there actually are multiple examples where you actually can get extremely bad complexities. Where, for example, if your tree was just a huge chain, and then you called the bottom of it, and then you wanted to roll back, and then you call the bottom of it again, and then you wanted to roll back. Essentially, every single one of those operations costs O of n, because you're essentially rolling back and doing an expensive operation a bunch of times.
Wait, so you're saying if you do merge by size and path compression, this is n log n?
Yes, it's still n log n, but it's just a lot worse in terms of constant factor and also it's a lot less clean to code.
Right. But just path compression is n squared.
Yeah, just path compression would be n squared. Yeah.
Oh, is this readable? It's in path compression, you can avoid these long chains. So if you just merge these two, and then merge these two, you end up getting a long chain. And then you call root at the bottom, let's say for a query. And then after that, they all point to the root. But then in rollback, you can just
You can just roll back the last one,
back.
and then you'll have to roll back all of these changes, and so it'll cost a lot of time.
Is there an example where it's n squared?
So
Wait, what
so,
do you mean? N squared for
n squared in total, right?
n squared in total?
So
yeah, I guess this is
imagine-
an example because if you do Q queries, the Q queries can just be do this once and then roll back, and then do this once and roll back, so then it'll be Q times n.
Yeah.
No, but doing it once means pairing each of, or joining O of n.
Say again?
So okay, wait. So your idea is
When you draw the arrow, this is O of n.
okay, wait. So imagine
yeah, this is O of n work
So you-
for one query.
wait.
What's your query?
The query was I want to call.
So imagine you have n minus 1 queries that create this structure, okay? And now you call a root or something, and then it creates this structure. And now you want to roll back.
Can you write the actual query?
Wait.
What?
Yeah. So the actual queries, let's say there's one more node over here. So let's merge merge 1 and 2, and then 2 and 3, 3 and 4, 4 and 5. And then we'll do one more merge, which is let's say 6 and 1. So then when you merge 6 and 1 in path compression, you call root on this node down here, and then all of these will now point up to the top, right? So that's n work, right? The merge will take n work, right? Yeah. So then the rollback will also take n work, right?
Yeah.
And then let's say we just
So what are
so-
your
so we merge 1 to 6, and then we roll back, and then we merge 1 to 6 again, and then we roll back. So let's repeat this like a million times or something. So then our total work will be like Q queries times n time.
Wait, so after you merge 1 to 2, you set parent of I equal to 2. After you merge 2 to 3, you set parent of 2 to be 1. Or parent of 3 to be 1.
No, right now I've just drawn 1 at the bottom. So parent of 1 becomes 2, parent of 2 becomes 3.
It's okay.
So I'm merging like 1 to 2 and then 2 to 3 and then 3 to 4.
Okay. And then when you join 1 to 6, you have parent of.
Yeah, so when I merge 1 to 6, parent of 1 becomes 5 or maybe 6.
Oh, 6.
Parent of 2 becomes 6, parent of 3 becomes 6, parent of 4 becomes 6.
Wait, what?
Wait, it's more so that parent 1 becomes
because-
5,
Oh,
parent
okay.
2 becomes 5.
Or because we call root on this function, and then in path compression, like the parent of each node will become the leader.
Yeah,
And
so
you'll
you
get
set
this
parent of
graph
5
here.
to 6.
Yeah,
And you also have this.
Okay, and then you roll back the 1 and 6 merge.
Yeah, then we roll back the 1 and 6 merge, so then it just goes from here back to here.
Or so you'd get rid of the parent of 5 equals 6.
Yeah, we get rid of the parent 5 equals 6, but then we also undo everything before.
Wait, why?
Because let's say we didn't roll it back, then how are we going to roll back?
Yeah, how are we going to do
How are we going
that?
to roll back again? Let's say when we roll back, we just don't actually roll back everything, but we just roll back the last thing. Then how are we gonna roll back 4 to 5? I guess here you can.
Wait, here you
We're really in the
can't.
parent array, parent of
Oh,
1.
here you can't. Yeah.
Parent of 1, 2, 3, 4 are all still 5.
Yeah.
Even after you merge 5 to 1 and 6. Or 2
yeah.
or 1.
So you could change the rollback process to not actually roll back everything, but then you run into a different issue. The issue you're running into now is that now that you haven't actually rolled back everything to the state it was before, and now when you want to undo 4 to 5, how are we going to undo 4 to 5 here? We could set 4 parent back to 4, but then that's actually incorrect because now you'll have this kind of component over here, but what you should actually have is just 4, 3, 2, 1 should have been its own component, and 5 as its own component. So you do actually have to roll back everything, and roll back and work. But
Well,
then,
your diagram should be or after you merge 1 and 6, all of the parents point to 6.
No, that's not true.
No, I think
No, because
you call the root
function
here,
before,
and they all
then-
point to the root, and then you
and then
merge
you have,
5 to 6. Yeah. So you call the root first here, and then everything points to 5, and then you call root at 6, which does nothing, and then the 5 points to the 6.
Wait, why can't I just undo parent of 5, I still have 5.
Yeah, that's what we were just doing here. So let's say we roll that back, and then 5 now points to 5. And now let's do one more roll back. Let's roll back 4 to 5. So the only thing we can do is just set 4's parent back to itself, right?
Okay, so
But this is actually incorrect now, because if we actually rolled back 4 to 5, what we should have left in our operations is 1 to 2, 2 to 3, and 3 to 4. And so 1, 2, 3, and 4 should be connected, but here 1, 2, 3, 5 are connected, which is not what we want.
okay, so specific example is merge 1, 2, 2, 3, 4, and then 1, 6, and then undo 1, 6.
Yeah.
4, 5, 4, 2, 0. Wait, do all of them and then undo them.
Sorry, what were you saying?
Right, there's just like untiered cases where you like merge each of these and then undo each. Rollback.
No, I'm just merging 1 to 6. I guess there's two things going on. Like, this is what I just showed is like why you have to roll back everything, right? So you can't actually just force parent back to itself. And now that we know we have to roll back everything, we can just merge this stuff together and then merge 1, 6, roll back, merge 1, 6, roll back, and do that a bunch of times.
Does anyone have any other questions?
Oh, yeah, that was a good question. Alright. Okay.
Okay. Feel free to start working on the problem set now.
Oh yeah, for the raffle, I'll be running my script in like a couple of minutes, so make sure you fill out this form if you haven't already. This is for last week. And then we'll give out the prizes.
Code I can actually just copy and paste and fill in latex later. It's an improvement over transcribing the statement.
Hey, how's it going?
Well, I just got a question here.
Is it about this?
No, I just came back from vacation, so it's my first day
In
class. I was wondering if like that can be added as an observer so I can catch up to the.
Oh yeah. So get back to you. Wait, do you want to pass your credit or
No, just
and then you can just you go to
A lot of today's problems are very Python unfriendly, by the way. We're uploading the first 2 problems to MIT IT Judge, so that those should be solvable. And then you can also work on previous day stuff. I think that's usually quite helpful.
So just fill that up.
Like the issue with Python isn't even just that it's slow, but for example, it doesn't have unordered set data structure, which most other languages have, which is useful for some of the problems. So like these two, like Python needs low and lack of ordered sets just makes it very hard to find small large problems for it. But it's okay, first 2 problems are on MIT IT Judge and you can also solve the problems from previous days. I think from yesterday most problems from like E to H have like a roughly similar difficulty.
This is like
somewhat
practice problems. Okay, yeah. Description.
Maybe cool. Wait, Harry, you have a computer now. Can we find better problems?
Okay. I will.
Yeah, like I don't want to look for problems anymore.
Oh, someone wanted me to. Okay, wait.
Oh, are you still here? Amina. Nice.
Okay. Okay, I can briefly re-explain dynamic connectivity for anyone who didn't exactly catch it the first time. Huh?
Sure, for this.
No need. So basically the idea behind how we approach this is that like if we have like a sample graph like okay, so if we have a sample graph like we have here, what we see is that we can actually reduce every edge to be active within a certain range, and that is like the range between its insertion point and its deletion point. So what exactly happens is essentially the the edge is only active within the range from 2 to 5 because it's inserted at 2, it's deleted at 6, and so it only exists within our graph during a range of times. And so we can use this to reduce it to a range query. And like, what structure do we use to solve range query? Well, very commonly we'll use a segment tree. And so the idea here is we add the edge to all of the like magenta blocks because that corresponds to that range within the segment tree. Like for example, if you were doing a query, those are the blocks you would look at to answer your query. And so what ends up happening is we just insert the edge into each of these blocks. So here we've inserted 1 to 4 into those blocks. Here we insert 1 to 3 into this block. And what ends up happening is the edge essentially is active. So like if an edge is at a node, it is active over the entire range from the left endpoint of that node to the right endpoint of that node. And so what we end up doing is we walk down the segment tree. So for example, once we go into this top level node, which contains 1 to 2, when we go down, no matter what subtree we're at, 1 to 2 is going to be present. So what we're going to do is we're going to add 1 to 2 at the very beginning when we visit the node, and then we can just keep it within our DSU for as long as we're recursing within this node. And as we start, answering queries and whatnot, once we leave this node, once we are done recursing and we want to leave this node, all we need to do is roll back this edge from that node, and we can keep going in a different tree. So for example, for a slightly deeper node, let's say you wanted to go here. So every time we're recursing within this node, that is highlighted in blue, we see that the edge 1 to 4 must be present the whole time. And so we add it at the very beginning when we enter this node, and we roll it back at the very end when we leave this node, so that every time we answer a query, for example, like over here, we answer a query within this node, we see that 1 to 4 is always inside it. So we're fine. And for here, 1 to 4 is inside it, so we're fine. And then once we leave this node, we can leave it, and then when we leave it, we roll back 1 to 4 from the node. Does that make sense to everyone? Yeah? Yeah. So, for example, you could have at time 2, I'm going to query are 2 and 3 connected? And then once you're at the leaf corresponding to time 2, you can just simply answer that query because you've constructed the DSU that exactly corresponds to that time. And I guess as a minor implementation note, generally what you're going to construct time over is you're going to construct time over all queries. And so every query is going to get its own time, whether it's an insert, delete, or just asking whether 2 things are connected or not. Yeah. Okay. Yeah. Have fun working on the problems from the problem set.